Hi, in this video, we are going to look at parametric equations for conic sections and for curves and even for straight lines and all. So this method of solving problems using parametric forms is useful because it reduces the number of variables in the system or in the problem that you are considering. So we'll show you the parametric forms for different types of curves, and then we'll apply it to a few problems so that you get the idea of how to do it. So for example, if we have straight lines, right? So we can say any point on a straight line, any point on a straight line can be represented by parametric equations like this. X is equal to x naught plus t cos alpha. Y is equal to y naught plus t sine alpha. Here, t is a parameter. T is a parameter, and the line passes through x naught y naught, through x naught y naught. How do we know that? We can see that x minus x naught is equal to t cos alpha and y minus y naught is equal to t sine alpha. So therefore, if you divide these two equations, you get tan alpha is equal to y minus y naught by x minus x naught. And actually, y minus y naught is equal to tan alpha into x minus x naught is basically the equation of a line with slope m is equal to tan alpha, right? So here alpha stands for the slope of the line, and this straight line definitely passes through x naught y naught, right? That point. So this is the parameterization. Any point on that straight line, suppose this is x naught comma y naught. If you go this side, let's say t is positive and this point is x comma y, t can be any parameter. And if you go on this side, you can say t is negative here. And you get another point here, right? Different values of t will give you different point coordinates. But the key thing to notice here is that x naught, y naught is a known value. So the only variable is t, because alpha is also known because slope of the straight line is fixed, right? So this is the parameterization for straight lines. Similarly, we can find parameterizations for other types of curves as well. So for example, for circles, we can easily show that x is equal to a plus r cos alpha and y is equal to b plus r sine alpha is the parameterization for a circle. Now this here alpha is the parameter. Alpha is the parameter, and the circle has radius r and center is a comma b. So it is very easy to show that this will result in a circle equation. So you can do that yourself. You just have to say that x minus a whole square plus y minus b whole square is r square. Similarly, for ellipses, what is the parameterization? So it is x is equal to x naught plus a cos theta and y is equal to y naught plus b sine theta. Here, theta is the parameter, and any point on the ellipse is going to be represented like this, right? And x naught y naught is the center of the ellipse. X naught y naught is center of the ellipse. 2a and 2b are lengths of major and minor axis. Major and minor axis. And basically the equation of the ellipse will become x minus x naught whole square by a square plus y minus y naught whole square by b square is equal to 1. This is the ellipse actually. X naught y naught becomes the center, 2a, 2b are the major and minor axis, and theta is the parameter, right? Similarly, we can get parameterizations for the hyperbola. Hyperbola's parameterization uses sec theta and cosec theta. It is x naught plus a sec theta and y is equal to y naught plus b tan theta. Sec theta and tan theta. Again, center is x naught y naught. X naught comma y naught. The real axis is 2a and imaginary axis or you can call it the transverse axis is 2a and the conjugate axis is 2b. So again, this is pretty standard stuff. And lastly, we have parabolas. The parameterization for a parabola, the standard parabola y square is equal to 4ax can be written with x is equal to at square and y is equal to 2at. Here t is the parameter, and 4 times a is the length of the latest rectum of this parabola, right? So we will see problems where we'll apply these methods, and you'll notice that using parametric methods reduces the work that is involved in solving the problem, right? Because it has a fewer number of variables there. Let's look at one question. A point P is on circle A, and the circle equation is x square plus y minus 1 whole square is equal to 1, and makes a counterclockwise rotation along the circle with a constant angular velocity. Okay. At the same time, point Q on circle x minus 3 whole square plus y minus 2 whole square is equal to 1 makes a clockwise rotation with the same angular velocity. With the same angular velocity. So both the rotations are with the same angular velocity. If initial positions of P and Q are 0, 2 and 2, 2 respectively, we have to find the maximum and minimum distances between P and Q. Find the maximum and minimum distance PQ. Okay. So here there are 2 points going around in circles. They are rotating on a circle. So let's draw a rough diagram. This is circle A. The center is here 0, 1, right? And the radius is 1. So this point is basically 0, 2. So notice that 0, 2 was the location of the point P. So P was starting from here and it was going this way, right? Now the starting point of Q was 2, 2. So that must be somewhere here. And the circle here, the second circle center is 3, 2. So the second circle center is 3, 2. So 2, 2 is here. So 3, 2 will be roughly here. And the second circle is like this. Radius of both the circles is 1. This is 3, 2. This is 2, 2. So this is point Q, right? And Q is going clockwise. Both have the same angular velocity. So the angle that they rotate will be same. So in equal time, this angle theta will be equal to this angle theta. Q will move like this, P will move like this, and both will describe equal angles theta in the same time t, right? Okay, so we will say, let's say P moves from here and goes to a point M, and angle PAM is theta. Let's say this is A and this is B, right? And Q goes to N, and angle QBN is also theta, right? And technically, you can give a sign to the angles because clockwise angles can be written as positive. So this will be positive angle. Here, anti-clockwise angle, actually I'm making a mistake. Anti-clockwise angles are usually given the positive sign. So this is positive and this will be negative angle, right? So what we can say, coordinates of M and N. Let's think of the coordinates of M and N using the parametric method. So the center here is 0, 1. So coordinate of M would be, basically it is making 90 plus theta angle, right? With this horizontal x-axis. So coordinates of M will be 0 plus 1 cos 90 plus theta, so pi by 2 plus theta, comma 1 plus 1 sine pi by 2 plus theta. This is the coordinate of M after it has rotated through theta angle, right? And coordinate of N, similarly, if you go this side, you are making angle pi minus theta with the horizontal here, right? Pi minus theta angle you are making with the horizontal. So you will start from 2, 2. So, oh no, but the center is 3, 2. So the parameterization will be 3 plus 1 cos pi minus theta and 2 plus 1 sine pi minus theta. That is the parametric method using the circle parameterization, which is x is equal to x naught plus r cos alpha and y is equal to y naught plus r sine alpha. This was what we had discussed in the previous screen when we are writing the parameterizations. Here x naught and y naught were the centers of the circle, right? So that's why we are putting 3 and 2 here. Once you have decided m and n, we can write the distance mn, and now it's basically a trigonometry problem. So distance mn is equal to, by distance formula, it will come out to be minus sine theta minus 3 plus cos theta whole square plus cos theta minus sine theta minus 1 whole square. And that can be simplified like this. It will become cos theta minus sine theta whole square plus 9 minus cos theta minus sine theta into 6 plus cos theta minus sine theta whole square plus 1 minus 2 times cos theta minus sine theta. That can be simplified further as 2 times cos theta minus sine theta whole square plus minus 8 cos theta minus sine theta plus 10, and that can be written as 2 times, think about it, cos theta minus sine theta minus 2 whole square plus 2. If you expand this, you will get the same thing. You can check that yourself. So what we do here is we rewrite this as root over 2 times. This is root 2 sine pi by 4 minus theta minus 2 whole square plus 2, right? So mn distance is coming out to be this, and mn distance is coming out to be this. So the maximum value will happen when this thing can become as large as possible. So one way to do that would be to make this minus 1, right? If pi by 4 minus theta is equal to minus pi by 2, this becomes minus root 2 minus 2 whole square, and the maximum value of mn will come out to be basically root over 14 plus 8 root 2. You can check that yourself. The minimum value of it will happen when pi by 4 minus theta is equal to pi by 2, and then this becomes subtracted. So the minimum value of mn comes out to be root over 14 minus 8 root 2, and this happens when pi by 4 minus theta is equal to pi by 2. So that is your answer for the question. The question is solved very easily once you set up the right parameters, right? So that is what you have to figure out here. That is what you need to learn. The next question that we look at is this one, question number 2. So let's look at this one. A straight line passing through M 2, 1 intersects x square by 16 plus y square by 4 equal to 1 at 2 points A and B such that M trisects the chord AB. Okay, you have to find the equation of the straight line. Find the equation of the straight line. There are normal standard ways to do this also, but I want to show you the parametric method. So we'll say let parametric equation of straight line be written as x is equal to, the straight line passes through this point, so we can use that, and we say 2 plus t cos alpha and y is equal to 1 plus t sine alpha. That is my parametric equation of the straight line, right? Now this is the straight line, and M is somewhere here, and we can say A is here and B is here. Why are we saying that? Because M trisects the chord AB, right? So the ratio can be written as 1 is to 2, right? This portion is 1 and this portion is 2. So we can say let the corresponding parametric values, corresponding parameters for A and B to be T1 and T2. What do I mean by that? So when you take different values of T, you should get different points on the straight line, right? So what I'm saying is, if you take T value as T1, you should get A point. And if you take T value as T2, you should get B point. Both of them are lying on the same straight line, right? But here, since you are going in opposite directions, and we know the ratio of 1 is to 2, we know a relation between T1 and T2. Because here the T is supposed to be the distance from this. The distance from the fixed point is the T, right? So we can say here T1 should be equal to minus T2. Because as I said earlier, what happens is if you go one direction, you can take it as positive sign. And if you go the other direction, you can take it as negative sign. And here T1, actually T1 is equal to minus T2 doesn't work because T1 is half of T2, right? So I should basically put here, my diagram is wrong. I want to keep using this T1 is equal to minus T2. So I should put this as B and A, right? This side is T1 and this side is T2. And this is 1 is to 2 ratio. So then T1 will be equal to minus of twice of T2, right? Minus 2 T2. Correct. So if you have this, we know that basically T1 plus T2 will be equal to what? T1 plus T2 will be equal to minus T2, and T1 T2 will be equal to what? T1 T2 will be equal to minus 2 T2 square. Just using this result that we have understood because of the nature of the section formula here, we get T1 plus T2 is minus T2 and T1 T2 is minus 2 T2 square. And therefore, we can write from here T1 T2 is equal to minus 2 T2 square, which is equal to minus 2 T2 square is T1 plus T2 whole square, right? Combining this and this, you get this result. T1 T2 is minus twice of T1 plus T2 whole square, right? Now we know that A and B are points on the curve, on the ellipse, right? So we can say that the general parametric point, the straight line, will intersect the ellipse. So we can put that in the ellipse equation. So let's do that, and we'll keep in mind this result that we have got. This result is satisfied for points A and B. So let's say the ellipse is here and the line is cutting it. This is my A and this is my B and this was my M, something like this, right? So we have the ellipse equation was x square by 16 plus y square by 4 equal to 1. And if you put t is equal to 2 plus t is equal to 2 plus t, x is equal to 2 plus t cos alpha and y is equal to 1 plus t sine alpha, these parametric equations into this ellipse equation, what we get is basically this 4 sine square alpha plus cos square alpha by 16 plus 1 plus t square sine square alpha. Okay, I have to put it properly. 1 second. Let's first simplify this equation. This becomes x square plus 4y square is equal to 16. So x square becomes 4 plus t square cos square alpha plus 4t cos alpha and plus 4 t square sine square alpha plus 8t sine alpha is equal to 16. This is my equation. So if you take t square common, you're getting t square and 4 sine square alpha plus cos square alpha plus, if you take t common, you get 8 sine alpha plus 4 cos alpha and you get minus 8 equal to 0. This is the equation, and from here we are getting t1 plus t2 is equal to minus of 8 sine alpha plus 4 cos alpha by 4 sine square alpha plus cos square alpha, and we are getting t1 t2 is equal to minus 8 by 4 sine square alpha plus cos square alpha, and we already know that t1 t2 is equal to minus of 2 times t1 plus t2 whole square. This is the result we have already established for the points A and B. So therefore the equation becomes minus of 8 sine alpha plus 4 cos alpha by 4 sine square alpha plus cos square alpha is equal to minus of 2 into t1 plus t2 whole square. So that will become okay, I have written it incorrectly. So basically I have to write t1 t2 is equal to t1 t2 is equal to this. So I'll just write it on the next screen. So I have t1 t2 is equal to minus of twice of t1 plus t2 whole square. So I get minus 8 by 4 sine square alpha plus cos square alpha is equal to minus 2 times 8 sine alpha plus 4 cos alpha whole square by 4 sine square alpha plus cos square alpha whole square. So this cancels here, the square goes away, this cancels here, this becomes 4, and you are getting 4 times 4, so 16 sine square alpha plus 4 cos square alpha is equal to 64 sine square alpha plus 16 cos square alpha plus 64 sine alpha cos alpha. This is the equation which, if you simplify, it becomes 48 sine square alpha plus 12 cos square alpha plus 64 sine alpha cos alpha is equal to 0. Dividing by cos square alpha, you get an equation in tan. You'll get 12 cos square alpha. Once you cancel 4, plus 12 tan square alpha plus 16 tan alpha plus 3 is equal to 0. This is the equation you get when you divide by 4 cos square alpha every term, right? So from here we can deduce that tan alpha is equal to minus 4 plus minus root 7 by 6, and therefore you get two different slopes. So the desired line equations will become y minus 1 is equal to minus 4 plus root 7 by 6 x minus 2, and the second line is y minus 1 is equal to minus 4 minus root 7 by 6 into x minus 2, right? So basically we are ending up with the two possible line equations such that you have the properties that it cuts the ellipse at 2 points, and also M is the point which is fixed and it trisects the chord, right? We use the parametrization of the straight line to do this, right? Okay. Uh, Basically, questions in conic sections can be solved using these kinds of parametrizations. The more you practice, the better it will be, and the more useful you will find these. Uh, Standard books like SL Loney have a lot of questions where you have to use this parametric equation. So you should try using those sources as tools for problem solving here. And in the next video, what we'll be doing is we'll be looking at something that is slightly more advanced, which is the families of curves. So the theory of family of curves is quite interesting, and many problems which look very difficult can be solved using family of curves properties. So we'll look at that in the next video, and hopefully that will teach you something that you have not seen so far. So stay tuned for the next video. I'll see you next time.